Imagine waking up one morning to discover that everything you thought you knew about your house was fundamentally incorrect. The walls you've been relying on aren't actually supporting anything. The foundation you've trusted isn't quite where you thought it was. And the blueprints you've been using to understand your home are filled with contradictions that no one can explain. This is essentially what's happening right now in cosmology, and the implications are staggering. For nearly a century, scientists believed they had cracked the code of the universe. We had equations that predicted how galaxies form, how space expands, and how matter behaves across cosmic distances. These theories passed test after test with flying colors. But in the last decade, something extraordinary has been happening. The universe has started to misbehave in ways that our best theories simply cannot explain. And the more sophisticated our technology becomes, the worse these problems get. What makes this moment so electrifying is that we're not talking about minor discrepancies or small measurement errors. We're talking about fundamental contradictions that strike at the very heart of how we understand reality itself. The kind of contradictions that historically have led to complete revolutions in human knowledge. Think about the moment when we realized the Earth wasn't the center of the universe, or when Einstein showed us that space and time are woven together into a single fabric. We might be standing at the threshold of another such revolution, and most people have no idea it's happening. Before we can appreciate why the current crisis is so profound, we need to understand what we thought we knew. The prevailing theory that has guided cosmology for decades rests on a few key pillars, and each one is now being questioned in ways that would have been unthinkable just 10 years ago. The first pillar is the cosmological principle, which sounds deceptively simple but is actually one of the most important assumptions in all of science. This principle states that if you zoom out far enough, the universe should look essentially the same everywhere. No matter which direction you look or where you are located, the large-scale structure and composition of the cosmos should be uniform. This isn't just the convenient assumption scientists made because it makes the math easier, though it certainly does that. It's a philosophical statement about our place in the universe and whether we can even hope to understand it. Why does this matter so much? Because if the cosmological principle is true, it means that our observations from this tiny corner of the universe are actually representative of the whole. We can be tiny creatures on a small planet orbiting an ordinary star in an unremarkable galaxy, and yet still make meaningful statements about the entire cosmos. We can peer through our telescopes, measure what we see in our local neighborhood, and extrapolate those findings to understand the universe as a whole. Without this principle, cosmology as a science essentially falls apart. We'd be like blind people touching different parts of an elephant, each coming to completely different conclusions about what an elephant is, with no way to know if our local measurements tell us anything useful about the bigger picture. The second pillar involves how we understand the universe's expansion. We've known since the 1920s that the universe is not static, but expanding. Every second, the fabric of space itself stretches, carrying galaxies away from each other. The rate of this expansion, called the Hubble constant, has been measured using multiple independent methods over the years. These measurements have given us crucial insights into the age of the universe, its composition, and its ultimate fate. For a long time, these different measurement methods agreed reasonably well with each other, which gave scientists confidence that they were on the right track. The third pillar concerns how structure formed in the universe. In the beginning, immediately after the Big Bang, matter was distributed almost perfectly uniformly. But there were tiny fluctuations, microscopic variations in density from one region to another. Over billions of years, gravity amplified these fluctuations. Denser regions attracted more matter, becoming even denser, eventually forming stars, galaxies, and galaxy clusters. This process follows well understood physics, and scientists can run detailed computer simulations that show how the universe should have evolved from that nearly uniform beginning to the complex cosmic web we see today. These simulations have been remarkably successful, reproducing many observed features of the universe with impressive accuracy. About 15 years ago, astronomers began discovering something deeply troubling. They started finding enormous structures in the universe that shouldn't exist according to our theories. These weren't just slightly larger than expected, they were grotesquely, impossibly large. Consider the giant arc, a structure of galaxies spanning more than 3 billion light years from one end to the other. To put that in perspective, light traveling at its maximum possible speed takes 3 billion years just to cross from one side to the other. Then there's a massive group of quasars stretching across 4 billion light years, a ring of galaxies measuring 5 billion light years in diameter, and perhaps most staggering of all, a wall of galaxies extending 10 billion light years, representing about 10% of the entire observable universe. These structures keep piling up, and each discovery makes the problem worse, not better. Why is this such a big deal? Because according to our cosmic theory, there's a fundamental limit to how large structures can be. The physics that govern how matter clumps together under gravity, combined with the expansion of the universe and the time available since the Big Bang, impose strict constraints. Beyond a certain scale, roughly around 1 billion light years, structures should blend together into a smooth, uniform distribution. The universe should transition from the lumpy, clumpy realm of galaxies and clusters to a homogeneous cosmic soup where no individual structures stand out. This limit isn't arbitrary. It emerges naturally from the cosmological principle we discussed earlier. If the universe is truly uniform on large scales, then structures can only grow so large before they become statistically impossible. Finding structures that violate this limit is like rolling dice and getting the same number 50 times in a row. It's not technically impossible, but it's so improbable that you'd be foolish not to suspect the dice are loaded. But the problem doesn't stop with structures that are too large. Astronomers have also discovered cosmic voids that are far more empty than they should be. These are vast regions of space containing far fewer galaxies than the cosmic average. And according to some surveys, we happen to be living inside one of these voids, a so-called local hole, measuring roughly 2 billion light years across. If this is true, it has profound implications. It means our local observations might not be representative of the universe as a whole. We might indeed be the ants sitting on the cherry, trying to understand a cake that tastes completely different everywhere else. Some scientists have tried to explain away these findings. They argue that when you're looking at such enormous scales, it's easy to see patterns that aren't really there, to connect dots that shouldn't be connected. They point out that the precise boundaries of these structures are often fuzzy and subjective. Different teams analyzing the same data sometimes disagree about whether a particular structure even exists. And with the sheer number of observations we're now making, we should expect to occasionally find some unlikely arrangements just by chance. But here's the thing. The structures keep appearing. Different teams using different telescopes and different analysis methods keep finding the same types of impossibly large features. The statistical evidence keeps mounting. And perhaps most tellingly, these discoveries aren't slowing down as our data improves. If these weren't just measurement errors or statistical flukes, we'd expect them to disappear as our observations became more precise. Instead, the opposite is happening. While astronomers were grappling with structures that were too large, cosmologists stumbled into another crisis, one that strikes at an even more fundamental level. This problem concerns the expansion rate of the universe itself, and it's so bizarre that it's been called the Hubble tension. The expansion rate, known as the Hubble constant, tells us how fast the universe is growing. It's measured in kilometers per second per megaparsec, which essentially means how much faster a galaxy appears to be moving away from us for every megaparsec of distance. Scientists have developed multiple independent methods to measure this crucial number, and for decades, these methods gave results that were close enough to each other that any differences could be chalked up to measurement uncertainties. But as technology improved and measurements became more precise, something strange started to happen. Instead of converging on a single agreed upon value, the different measurement methods started to diverge, and not just by a little bit. The discrepancy has grown to the point where it can no longer be ignored or explained away as experimental error. On one side, we have measurements based on the cosmic microwave background, the afterglow of the Big Bang that fills all of space. By studying tiny temperature variations in this ancient light and plugging those observations into our cosmological models, scientists calculate that the expansion rate should be about 67 kilometers per second per megaparsec. On the other hand, we have measurements based on observing nearby supernovas and other cosmic distance markers. These observations suggest the expansion rate is about 73 kilometers per second per megaparsec. At first glance, 6 units might not sound like much of a difference. But in science, what matters isn't the absolute size of the disagreement, but how significant it is compared to the uncertainties in each measurement. Both methods have been refined to the point where their error bars are tiny. The chance that this mismatch is just a statistical fluke has been calculated to be less than 1 in a million. In scientific terms, this is what's called a high sigma discrepancy, meaning it's extremely unlikely to be due to random chance. Think about it this way. Imagine you're measuring the speed of a car using 2 completely different devices. Your GPS says 73 miles per hour. Your speedometer says 67 miles per hour. You double-check both devices multiple times. You calibrate them. You have independent experts verify that both are working correctly. And yet, they continue to give you different readings. At some point, you have to conclude that something is fundamentally wrong, either with one of your measurement devices or with your understanding of how speed works. The universe is doing exactly this to us. It's giving us 2 different answers to the same question, and both answers appear to be correct based on the methods used to obtain them. This is deeply unsettling because it suggests that there's some systematic error in one of our measurement techniques that we haven't identified despite years of scrutiny. Or our basic model of how the universe works is missing something crucial. Some scientists have tried to explain away these findings. They argue that when you're looking at such enormous scales, it's easy to see patterns that aren't really there, to connect dots that shouldn't be connected. They point out that the precise boundaries of these structures are often fuzzy and subjective. Different teams analyzing the same data sometimes disagree about whether a particular structure even exists. And with the sheer number of observations we're now making, we should expect to occasionally find some unlikely arrangements just by chance. But here's the thing. The structures keep appearing. Different teams using different telescopes and different analysis methods keep finding the same types of impossibly large features. The statistical evidence keeps mounting. And perhaps most tellingly, these discoveries aren't slowing down as our data improves. If these were just measurement errors or statistical flukes, we'd expect them to disappear as our observations became more precise. Instead, the opposite is happening. Just when cosmologists were struggling with structures that are too large and an expansion rate that won't cooperate, the James Webb Telescope entered the scene and immediately threw another wrench into the works. Launched in late 2021, This technological marvel can peer deeper into space and farther back in time than any telescope before it. Scientists eagerly anticipated the discoveries it would make about the early universe. What they didn't anticipate was that it would almost immediately start finding galaxies that shouldn't exist. The James Webb Telescope specializes in infrared light, which allows it to see incredibly distant galaxies. Because light travels at a finite speed, when we look at distant objects, we're seeing them as they were in the past. The most distant galaxies visible to James Webb appear as they were when the universe was just a few 100 million years old, less than 3% of its current age. This is the cosmic dawn, the era when the first stars and galaxies were forming, and it's a period that scientists have desperately wanted to observe in detail. What they found has been shocking. Some galaxies appear to have formed astonishingly quickly, showing up in images that correspond to just 280 million years after the Big Bang. This is far earlier than our models predicted. According to our understanding of structure formation, galaxies grow through a hierarchical process. Small clumps of matter emerge to form larger clumps, which merge to form still larger structures, and so on. This process takes time, lots of time. The first large galaxies shouldn't have appeared until at least 500 million years after the Big Bang, and finding fully formed galaxies significantly earlier than that presents a serious challenge to our timeline. But the problem goes even deeper than just the existence of these early galaxies. Some of them appear to be too mature for their age. When the universe was young, it consisted almost entirely of hydrogen and helium, the simplest elements. Heavier elements like carbon, nitrogen, oxygen, and iron were only created later inside stars through nuclear fusion. When massive stars exploded as supernovae, they scattered these heavy elements into space, enriching the gas that would form the next generation of stars. This means that the very first stars and galaxies should be almost entirely devoid of heavy elements. The second generation should have a little bit more. The third generation more still. It's a progressive enrichment process that takes many generations of stars living and dying. Yet, some of the early galaxies observed by James Webb contain significant amounts of heavy elements. This implies that multiple generations of stars had already lived and died before these galaxies formed, which pushes the timeline even further back and makes the problem even more acute. It's as if you walked into a kindergarten classroom and found teenagers sitting at the desks. Not only are they there when they shouldn't be, but they're already showing signs of maturity that should take years to develop. Either these cosmic children grew up and fast forward, or something fundamental about our understanding of the early universe is wrong. Some scientists have proposed that maybe the first stars were much more massive than we thought, burning through their fuel and exploding much faster than normal stars. Others suggest that perhaps dark matter, the mysterious substance that makes up most of the matter in the universe, behaved differently in the early cosmos than it does today. Still, others wonder if our dating methods might be slightly off, though this would require errors large enough to be unlikely. What's particularly frustrating is that these aren't isolated anomalies. As James Webb continues its observations, it keeps finding more and more of these problematic galaxies. The sample is growing, and with it, the challenge to our theories becomes harder to dismiss. This isn't just one or two weird objects that could be explained as statistical outliers. It's a systematic pattern, suggesting that galaxy formation in the early universe worked differently than we thought. The three major cracks we've discussed are striking enough on their own, but they're not happening in isolation. They're part of a broader pattern of discrepancies that have been accumulating over the past decade. Each one might seem solvable on its own, but together they paint a picture of a theory under serious strain. Consider the lithium problem, which has been puzzling scientists for decades. According to our calculations of what happened in the first few minutes after the Big Bang, when the universe was hot and dense enough for nuclear reactions to occur. A specific amount of lithium should have been created. We can calculate this number with considerable precision based on well-understood nuclear physics. The problem is that when we look at the oldest stars in the universe, which should preserve the primordial chemical composition, we find only about 1/3 as much lithium as predicted. 2/3 of the universe's lithium has seemingly vanished, and nobody can explain where it went. Then there's the core cusp problem, related to dark matter. Dark matter is the invisible substance that makes up most of the matter in the universe. We can't see it directly, but we can observe its gravitational effects on visible matter. According to our simulations, dark matter should pile up very steeply at the centers of galaxies, forming what's called a cusp in the density profile. But when we measure the actual rotation of stars and gas in many galaxies, especially smaller ones, we find that the dark matter distribution is much gentler, forming more of a flat core than a steep cusp. This could mean our simulations are missing some important physics, or it could mean our understanding of dark matter itself is incomplete. Perhaps most intriguing of all is the recent suggestion that dark energy might not be constant. Dark energy is the mysterious force that's causing the expansion of the universe to accelerate. Since its discovery in the late 1990s, scientists have assumed that dark energy is a property of space itself, a cosmological constant that doesn't change over time. But last year, one of the largest galaxy surveys ever conducted released results suggesting that the strength of dark energy might have varied throughout cosmic history. If confirmed, this would be revolutionary, completely changing our understanding of the universe's past and future. The survey measured the positions and properties of millions of galaxies at different distances, corresponding to different epochs in cosmic history. By analyzing these patterns, scientists can infer how dark energy has influenced the universe's expansion over time. The preliminary results hint that dark energy might have been weaker in the past than it is today. This would overturn one of the key assumptions in modern cosmology and would require a complete rethinking of what dark energy actually is. Even things that seemed settled beyond any reasonable doubt are now being questioned. The cosmic microwave background, the afterglow of the Big Bang, has been studied in exquisite detail. Its patterns and temperature variations have been mapped with incredible precision, and for years it was considered our most pristine window into the early universe. But now, some scientists are wondering if those early galaxies we discussed might have been bright enough to slightly contaminate the cosmic microwave background signal. If true, this would mean we've been misinterpreting one of our most important data sets. What makes this accumulation of problems so significant is that they're not all pointing in the same direction. It's not as if we could add one new ingredient to our cosmic recipe and solve everything at once. The structures that are too large suggest the universe might be lumpier than our theories allow. The Hubble tension might require new physics in either the early or late universe. The early galaxy suggests that structure formation happened faster than we thought. These problems don't have an obvious common solution, which makes the situation both frustrating and fascinating. When faced with observations that don't match theory, scientists have historically responded in two fundamentally different ways, and the question of which approach is appropriate now is at the heart of the current debate. The two scenarios are often called the Neptune moment and the Mercury moment, named after the historical examples that define each approach. The Neptune moment refers to a triumph of 19th century astronomy. Astronomers noticed that the planet Uranus wasn't following the orbit predicted by Newton's laws of gravity. Its path through the sky showed strange deviations that couldn't be explained. But instead of abandoning Newton's theory, astronomers suggested that an unknown planet beyond Uranus might be tugging on it gravitationally. Two mathematicians working independently calculated where this hypothetical planet should be based solely on Uranus's orbital irregularities. When astronomers pointed their telescopes at the predicted location, there it was, Neptune, exactly where the mathematics said it would be. This was a stunning vindication of the existing theory. The solution wasn't to change the laws of physics, but to recognize that there was more matter in the solar system than had been accounted for. The Mercury moment tells a very different story. Like Uranus, Mercury also showed orbital anomalies. The point of its closest approach to the Sun, called the perihelion, was slowly rotating in a way that didn't quite match Newton's predictions. Astronomers tried the same trick that had worked with Neptune. They proposed the existence of a planet closer to the Sun than Mercury, which they even named Vulcan. Searches were conducted, reports of sightings were made, but Vulcan never materialized. The solution to Mercury's orbital problem didn't come from finding more stuff. It came from Einstein's general theory of relativity, which completely reimagined how gravity works. Once Einstein's theory was applied, Mercury's orbit was explained perfectly, with no need for an undiscovered planet. The question facing cosmology today is whether we're in a Neptune situation or a Mercury situation. Are the current problems signs that we're missing some component of the universe, some form of matter or energy that we haven't detected yet? Or are they signs that our fundamental theories need to be replaced with something deeper and more accurate? Some scientists lean toward the Neptune interpretation. They argue that we should be conservative, making minimal modifications to our successful theories. Perhaps there's a new type of particle that interacts differently with gravity than we expected. Perhaps dark matter has properties we haven't accounted for. Perhaps there's an additional field or force at work on cosmic scales. These solutions would extend our current theories rather than replacing them, adding new ingredients while keeping the basic recipe intact. Others argue that we're facing a Mercury moment, that the accumulation of problems is too severe to be solved by minor adjustments. They point out that many of the proposed fixes feel ad hoc, designed specifically to solve one problem without any independent motivation. They suggest that we might need to fundamentally rethink our approach, perhaps modifying how gravity works on cosmic scales or reconsidering our basic assumptions about the structure of space and time. History suggests that Mercury moments are rare but transformative. Most anomalies in science are resolved by finding missing pieces rather than rebuilding the entire puzzle. But when a revolutionary change does occur, it opens up entirely new ways of understanding reality. Einstein's relativity didn't just fix Mercury's orbit. It revealed that space and time are interwoven, that mass warps the fabric of space-time, and that seemingly absolute concepts like simultaneity are actually relative. It was a complete paradigm shift that changed not just astronomy, but all of physics. The challenge is that we can't know in advance which situation we're in. Neptune and Vulcan looked like similar problems at the time. It was only through decades of searching and theoretical work that the true nature of each became clear. We're living through that period of uncertainty right now, and the outcome will shape the future of cosmology for generations to come. Right now, the cosmology community is engaged in intense debate about what these problems mean and how to address them. This isn't a calm academic discussion happening in ivory towers. It's a fierce intellectual battle with reputations, funding, and fundamental questions about reality at stake. On one side are those who argue for patience and caution. They point out that extraordinary claims require extraordinary evidence, and that history is littered with supposed crises that evaporated with better data. They note that the cosmological standard model has been incredibly successful for decades, passing numerous stringent tests. Abandoning it based on a handful of discrepancies, they argue, would be premature and possibly foolish. They're working to find errors in observations, refine measurement techniques, and develop conservative extensions to existing theories that can resolve the problems without requiring a revolution. On the other side are those who believe the time for minor adjustments has passed. They argue that the accumulation of evidence is too substantial to ignore, and that clinging to the old model in the face of mounting contradictions is itself unscientific. They're exploring radical new ideas, modifications to gravity, new forms of dark energy, alternative explanations for cosmic expansion, even suggestions that some of our most basic assumptions about the universe might be wrong. They see this as an exciting opportunity to break free from old paradigms and discover deeper truths. Between these extremes are many scientists taking more nuanced positions, acknowledging the problems while remaining uncertain about their implications. They're doing what scientists do best, making more observations, conducting more experiments, and testing hypotheses rigorously. The James Webb Telescope continues to probe the early universe. New surveys are mapping cosmic structure with unprecedented precision. Improved measurements of the expansion rate are being made using novel techniques. Each new piece of data has the potential to either resolve the crisis or deepen it. What makes this moment so fascinating is that we genuinely don't know how it will turn out. Will the problems disappear as mirages, artifacts of incomplete data or flawed analysis? Will they be solved by incremental improvements to our theories, adding new ingredients without changing the basic framework? Or will they force us to tear down our current understanding and build something entirely new? The uncertainty itself is valuable. In science, periods of crisis are when the most important progress happens. When theories are working well and matching observations, science proceeds steadily but slowly, filling in details and refining calculations. But when observations and theory clash dramatically, that's when revolutionary ideas emerge. That's when young researchers challenge established wisdom. That's when the field is forced to confront its assumptions and think creatively about alternatives. If there's one thing we should take away from this moment in cosmology, it's that uncertainty is not weakness, but strength. The universe is revealing itself to be more complex, more surprising, and more interesting than we imagined. Our best theories, which seemed so solid just a decade ago, are being stress tested in ways we never anticipated. And rather than being a cause for despair, this is cause for excitement. We're living through a time that might be remembered centuries from now as a turning point in human understanding. Whether we find a cosmic Neptune or a cosmic Mercury, whether we need small adjustments or revolutionary change, the outcome will deepen our knowledge of reality. We'll understand better where we came from, what the universe is made of, and where everything is heading. The cosmos is speaking to us, telling us that our story is incomplete. It's showing us anomalies and contradictions that demand explanation. And scientists around the world are listening, thinking, and working to solve these puzzles. In the end, that's what science makes so powerful. It's a self-correcting system that embraces challenges and revises itself in response to new evidence. The universe might be misbehaving, but it's still following rules. Our job is to figure out what those rules actually are. And right now, for the first time in decades, we truly don't know what we're going to discover. That's not a crisis of science. That's science working exactly as it should. The universe is about to get a lot more interesting, and we have front row seats to watch it happen.